But I won't be like overly picky, hopefully, on significant figures. So, 1126 kilojoules. Now, did it tell us, so how does this 35 grams of ammonia come in? Well, when you do this reaction, you produce 1,144 kilojoules of energy. But how many moles of ammonia did that use? 2. And how many moles of ammonia are we actually going to use? 2.06. So even though there's hardly any difference between 2 and 2.06, there actually is. So what you're going to say is there's 1,144 kilojoules produced every time you burn 2 moles of ammonia, or produce, or whatever, we're producing ammonia. So then you have to figure out how much is actually produced for the real amount of ammonia that you use, right? So then we end up with energy, Micah.
There is an error for the enthalpy of, let's see, I think it was water, because you have negative 986 when it should be negative 968.
Ooh. Did I do it right on the calculator? Hold on. 242 times 4, 968. Minus 9.8. So I get negative 1060 here. 60.
Yes.
Okay. Minus 66.4. So 1126.
That's what I got without.
Okay.
There.
Good. So then we'll go here. 1126. And now we say, okay, this much was produced when 2 moles of ammonia was produced. What about if 2.06 was produced? So then you just divide by 2, multiply by 2.06, which is hardly any different anyway. And you get negative, and then how many can I keep? So how many can I keep? 3 because of this.
My answer was right.
Well, your question was, you must have just not written the whole thing up or something. I'm confused.
Wouldn't the
Okay.
negative 126 kilojoules, wouldn't that, because it's negative, it'd go on the product side?
Yeah.
So
Yeah.
it would be positive when you're putting it,
You have to plug it back in.
yeah, put it back into the little equation.
Hold on.
Because we both got positive answers.
Yeah.
That's why.
Let me think. Let me do my significant figures first, and then I'll think about why I'm wrong. Okay. Why am I wrong again?
Because negative 1,
That's exothermic, so you need to put that on the product side of that original balanced chemical equation. That's what the book teaches you do. Like earlier in the module, like you put it on the product side, or if it was endothermic, you would put the energy on the reactant side. So because that's negative, you would put it on the product side, and then you would plug it back into like a moles conversion, or the energy / moles conversion.
Like that?
And how does that change the sign?
Yeah, change the sign.
I said, how does it change?
Let me think.
Because if you don't keep the
Oh.
negative when you put it on the product side. You just yeah.
Okay, so this is essentially semantics. The question says, how much energy will be released? Okay, well, when energy is released, enthalpy is negative, because that's a definition of exothermic. So if I'm literally writing how much energy will be released, I would say 1,160 kilojoules of energy will be released. But if I just, can't spell released, if I end up with a negative answer, by definition, that is energy being released because it's a negative enthalpy. So, if you want to follow the steps in the book, that's fine. If you just want to think like negative enthalpy means it's exothermic energy is being released, that's fine. It's all the same thing. So, are there any questions about this extraordinarily confusing problem? All good? Okay. What? Saul, we're on 7.
I had a question.
Okay, go ahead.
When he asked for energy, like how much energy, that just means find delta H, right?
Yes, yes.
Delta H, the thing.
Yes, standard enthalpy of formation. So the little thing means standard and the F means formation. And that just means you have permission to use the chart. If it weren't at standard conditions, you would need a different chart. They publish every couple of years a book that's literally this thick, and it has enthalpies for whatever temperature your lab happens to be at that moment, and it's a nightmare. You're better off to just control your conditions, in my opinion, but if not, there you have it, or if you're working outside or something. So how's it going?
It's good.
All right, put it up, and then we'll work on it. But yes, if the test has the little degree sign by the enthalpy or entropy, you have to produce a number. And if it doesn't, then you just produce a negative or positive description.
You want me to write it up on the board?
Yes.
So even if it doesn't ask for the sign, it doesn't have the circle at the top, it'll be sign.
I think if it doesn't have the circle, it's essentially not giving you permission to use the chart, and you don't have to get a number. But if you can get a number, please get one. I mean, I think use common sense. Get a number if you can. If he gives you phase, use Hess's law. If he doesn't, he'll most likely say use bond energy for enthalpy. But for entropy, you only, if he just gives you a chemical equation and no numbers, you're likely going to just get a sign. But if he gives you numbers, it'll probably have a little degree sign, and you'll need to use the chart and get a number. Confusing. All right, so I've lost my page, and we're talking about entropy now. Okay. So Saul's problem says, what is the change in entropy of the following reaction? So we could probably figure out if we're going to expect a positive or negative answer before he goes about it. So he's got a liquid plus a solid gives us a solid. So would we expect entropy to be increasing or decreasing? Decreasing, because you're losing liquid, moving to all solid. Liquid is more chaotic than solid. So I would think that we're going to be, entropy is going to be decreasing here. So if I don't get an answer that's negative, I'm going to check my work. How many practice problems were there? Okay, so I'm missing a page somewhere. So it's coming up soon, probably. Works, maybe I'll find the page.
Are you going to collect the lab?
Yes, I'll collect, and I handed out stuff. Yes, make sure I collect stuff. And you guys didn't take a test, all my other classes did. All right. I'm going to turn around and look at what's happening here. So he's got, I'm going to write the balanced equation above there, I think. So he took entropy of the products. There's only one. solid, and that is so, and it's balanced, all coefficients of 1. So he took 1 mole of water times its entropy. Okay, hold on. Oh, that is a balance equation. Oh, he just plugged in numbers to keep us all straight. So, this one is entropy of water and entropy of calcium oxide. And he found that. So this
This
is
is negative. I put it in the answer, but I forgot to put it in the question.
and then products was that. So if you take, just for my sake, so if we find entropy to be products, it's always good to write your equation for my benefit, if nothing else. Products, you found it to be 76.1,
Yes.
and there's 1 mole, so you cancel out. So you're getting what, joule per Kelvin or something?
Oh yeah, joules over moles times.
Okay, because the 1 mole will cancel out the mole minus the reactants, and you got
Negative 32.
oh, okay.
I have it up, the big
So,
answer there.
this is the water, that's the calcium oxide, and it's a negative 32,
Yeah.
and that is joules per Kelvin, because each one is 1 mole, so the moles cancel in the balanced equation. And if I double subtract, that means I end up adding them, and I get what? When I do that, I get 76.1 plus 32. I get 108-ish. Is that right? And they both have a tenths place. Hopefully they should. And what I got. Not what I got. So let's go hunting for a mistake. Let me know if anyone spots it, because I haven't spotted it yet and I can't find my chart. Alright. So we're using table 13.3. Calcium oxide is a solid, is 38.2. Alright, so if I write it, I'm going to do products. So I would do 1 mole of calcium oxide times 38.2 joule per mole degree Kelvin.
I think I already see.
And that is, oh, that's a reactant. Okay, a little bit better. So, product, calcium hydroxide is a solid, so 76.1 joule per mole Kelvin times 1 mole of calcium hydroxide. And that is the only product minus this whole big thing, which I'll put in a big bracket.
I think I see why the answer
Do we?
is.
Plus, the other reactant is water liquid. Water liquid is 69.9. It's 1 mole of it. Now, that whole line is one thing. So 76.1 joule per Kelvin.
Oh, I see. First of all, the reactants, I don't know why there's a 32.0, because technically it should be 108, and it's not negative.
Hold on. Did I use the wrong chart?
Because of all standard absolute entropies are always positive, never negative.
I don't have a negative, do I?
The reactants have, you made it a negative, and then when you subtracted the negative, I'm not talking about your new product. I'm talking
Yeah,
about
I
the
don't,
old
yeah,
one.
the old one isn't quite right. But the new one.
Yeah, the new one's gonna be right.
Okay, good.
It should be right.
38.2 joule per Kelvin plus 69.9 joule per Kelvin. Alright, so if we get 38.2 plus 69.9, 38.2 plus 69.9. So this is 108.1 joule per Kelvin. And I end up subtracting, so I'm gonna end up with a negative. And I get, now I have to think through significant figures, because my calculator just gives me 32, but I can see significance in both the 10th place, so I need to keep a 10th place even if it's a 0. Joule per Kelvin. So, my entropy is negative, is that what I expected? Yes. So I get negative 32.0 joule per Kelvin. I expected a negative entropy because it got less disordered, more orderly because it formed a solid product, and that liquid was disorderly in the reactants. Oh, that's a hard one.
All these are
But number 8's the real kicker. Sorry, Lily. And this is very, very similar to what's on your test. Any questions about 7 before we move on? Okay. So 8 says the enthalpy of a certain reaction, we wrote all over that. The enthalpy of a certain reaction is negative 1,023 kilojoules per mole. So is it exothermic or endothermic? Exothermic. Negative enthalpy means exothermic. Memorize that. That definition will just really help you to think through what's happening in all these problems. So, okay. Delta S, so entropy, is negative 324 joule per mole Kelvin. So negative entropy, are we becoming more or less orderly? Less orderly. So we have an exothermic reaction that's becoming less orderly. That makes sense, at least, right? What is the temperature range for which it's spontaneous? Okay, so spontaneous means Gibbs is negative. So these are all definitions you've got to know, right? Entropy is negative, things are becoming more chaotic. Enthalpy is negative, it's exothermic. Gibbs is negative, it will be spontaneous. So, do you want to put it up? Okay. I'm actually, while she's putting it up, I'm literally going to have a look at the test packet. And I know that there's a wonderful hint I can give you on this question, and I just have to see what it is. Maybe it just has what it is. Okay. So here's your hint for the test question that is kind of the inequality situation that you have to set up. If delta H is negative, that means you've got an exothermic process. Would you expect Gibbs to be, no, not Gibbs. Would you expect entropy to be positive or negative for an exothermic reaction?
Well, it's increasing entropy technically, because when you add more energy, things get more crazy, gases happen more. So it would be negative because you're decreasing order.
Yes, so what you would expect is truly what happens on the test. So when you have to set up an inequality on the test, it's going to be for an exothermic situation. And entropy should be negative. Things should be getting more chaotic for an exothermic process. That's what you expect, that's what you should see. If you don't get a negative entropy, try again. But do your best and show your work. I give partial credit if you copy the wrong number off the chart or forget a mole somewhere or something. Show your work and it won't be like a catastrophic miss the whole question.
So exothermic will be lower, like a negative.
Entropy will, tell me again. My brain is
well,
working.
from the way I just using stream of conscience, a negative entropy would be an increase in disorder
Okay,
or a decrease in order.
Okay,
Which
so,
can confuse you, so.
yes,
just-
entropy should be negative for an exothermic process. You should get a negative answer for that problem. It's like, it's the only one you'll need an inequality for. All the others are just regular old problems. So, delta H is negative for exothermic.
Yeah, I think you just move.
Delta S should also be negative.
I think you just move it over instead of dividing that.
This right equation. So teach me. All right, so Lily thinks completely differently about math than I do because she rearranged that correctly, but it's just differently than I decided to. So she is trying to figure out what to do about temperature to get a negative Gibbs, maybe? What do I do about temperature to make sure